Now, let me introduce you guys to the typical workflow of Scikit-Learn. In Scikit-Learn, the typical workflow will contain 4 steps. I will be illustrating that 4-step procedure using perhaps one of the simplest supervised learning algorithm. So the algorithm is k-nearest neighbors. In short, in abbreviation, we call it KNN. So in the KNN algorithm, essentially we're trying to get the k-nearest neighbors to vote. So let me just expand the intuition and then we will get to the 4 steps. The intuition is that basically for this KNN algorithm, we are trying to predict the outcome variable of each of the observations, right? So when we are doing the prediction, the first step we're going to do is that we are going to calculate the distance between our desired point and all the other points. Let's say, for example, here we try to make a prediction for this top point here, the point at the top right corner, the green one here. Then what we are going to do is that we are going to calculate its distance with other points. And then we are going to pick the k nearest points to that point. And so that's the first step. And the second step is that we are going to let all the k nearest neighbors to vote for the category of this top green dot here. For example, let's also still use the iris dataset example here. Let's say the k neighbors of this top point, like let's say they are all versicolor, so they all have labels as versicolor. Then their vote is that actually this top point is also a versicolor. So that majority vote is going to be our prediction for this particular observation. So that's the intuition behind the KNN algorithm. Then let me introduce you guys to the procedure of the Scikit-Learn workflow. The step 1 is that we are going to import the class we plan to use. It might be a little bit hard to comprehend what a class is for you guys at this stage. So you can just think of it as a template for an object. Essentially, you are creating a class because you want to reuse it to create similar objects. So that's the whole reason for class. And one feature with Scikit-Learn is that it sort of stored all the machine learning algorithms as a class. So we are going to create our model as an object based on those classes, based on those templates. Therefore, step 1 is that we're going to import the class we desired. Here, from sklearn.neighbors, we are importing the k-neighbors classifier. So that's a class name for the KNN. Let's move on to step 2 here. For step 2, it's instantiate the estimator. So by instantiate, I'm basically referring that I'm going to create an object based on the class. In other words, make an instance of this model. Of course, when we are creating the object, we need to pass specification of parameters to the class. So here for the KNN example, we are going to pass a key parameter, basically k. So we need to pass the number of the closest neighbors to our KNN class. When we are doing the instantiating, we create a new object called as KNN, and we let KNN being equal to k neighbors classifier, and we pass on the property that is k equal to 15 to the class. So basically this line of code here is doing all the instantiating, and then we can also print KNN. So that's the step 2 here. Now let's move on to step 3. So here, that's actually where we are doing the training of our machine learning algorithm. So here we are letting the algorithm to try to learn about the relationship between the features and the outcome variable. Because here we are doing supervised learning, right? So here we let x being equal to iris.data. Remember, that's the features, right? And we let y being equal to iris.target. Remember, that's the iris types, which is denoted in 0, 1, and 2. And we already created our model as this KNN. Now we actually have to feed that model, or we have to train that model. And we are doing the training or the fitting via this method called fit. So KNN.fit. And the two inputs we input into the KNN model are going to be X and Y. So basically the data and the target. So the features and the outcome variable. So here, that's sort of a visualization of the KNN algorithm results. Basically, you can see that those colors, the orange and the light blue here, and also this darker blue here, those are representing the predictions of the KNN models. And also those points are actually representing the actual types, the actual labels of our data. So for example, the orange dots, those are setosa, and the light blue dots, those are the actual versicolor, and the darker blue dots are like virginica. So those darker blue points, those are actually virginica. So basically, our model is doing a relatively job in terms of distinguishing setosa from the other two types. So it's able to predict the types of setosa almost perfectly. But our model somehow fails, not really fails, but not doing that good a job distinguishing between versicolor and virginica. So it actually got some observations wrong. So here, for example, this dot is actually a virginica, but our model actually labels it as a versicolor. Now let's go to step 4. So easy, right? So the training is actually just done by a simple line of code, just by the fit here. Now, step 4 is about predicting. So meaning that we can feed observations into our trained models. By doing this line of code, we finish our training. Our model KNN now is trained. So we can feed new observations into that trained model and to basically to generate predictions. So in the Scikit-Learn workflow, you just do the prediction via this predict method of the basically of your model. So here we try to first make a prediction for a single observation. So we first create this single observation. So we let new flower being equal to this data. So this observation has sepal length of 3, sepal width of 5, petal length of 4, and petal width of 2. So that's new flower. That's our single observation. And now we just feed that new observation, that single observation into our model. So knn.predict and then new flower. So it returns this array and it says 1, meaning that it predicts our new observation here to be versicolor. Also, we can utilize, whenever we are doing the prediction, we can also actually check the probability of each category. So here, and we are checking that probability using this method here, predict proba. So knn.predict proba, and then you are inputting new flower. And then the result returned is that the probability for the first class is 0. And the probability of the second class, the versicolor, is going to be the highest and being 0, 8, 7-ish. And for the probability of this new observation being a Virginica, that's going to be 0.1333. So that's essentially consistent with our prediction about the category directly, right? So our prediction about the category is that it's the versicolor. And also if we check the probability of each individual category, actually the versicolor also has the highest probability. So that's a prediction based on a single observation. We can actually do a prediction for multiple observations at the same time. So now let's try out the case of 2 observations. So now we let our data set being new flowers, and we let new flowers contain 2 observations. And then we directly feed those 2 observations or the new flowers into the predict proba method. Then that's what we have. Oh, sorry, I didn't define the new flowers first. So after defining the new flowers, then we execute this code here again. So here, let me interpret the results for you guys. So the first line here, that's corresponding to the probability for our first observation. For our first observation, the probability prediction is the same as the previous cell. And then for the second observation, the predictability is that they basically like it has the equal probability of being the versicolor or the setosa. So as you can see, the probability is kind of equal here. And then for the third category, which is the Virginica, it actually has the lowest probability. So basically, the second observation is not likely being a Virginica at all because it has a lowest probability that is very close to 0. Now, let me also explain validation here. So for validation, it's all about, remember the overfitting risks we talked about earlier. So for overfitting risks, essentially we are trying to, so whenever we are avoiding overfitting risks, we are trying to avoiding that our models, our algorithms are actually just memorizing the data set too well, and it fails to generalize. So basically it just memorizes the data it has seen, and it performs terribly on the data set it has never seen. So that's the so-called overfitting risk. So the validation here is all about avoiding such overfitting risk. The core idea for validation is that we're going to do a partition on the data set. And for example, we partition the data set into 2 parts, one being a training data set, and the other part being a testing data set. And we will only be letting the algorithm, the model, to look at the training data set to try to memorizing the training data set. And we are actually going to evaluate that model's performance on the testing data set it has never seen. So that's the basic idea for model validation. So you are doing training on a part of the data set, and then you are doing the model evaluation on the other data set that the algorithm has never seen. Now let's directly go to train test split. So here, let's take a look at the shape of our data. So we print text or shape, and we print white or shape. So we can see that the X actually has 150 rows. So because we have 150 observations, and it also has 4 columns. Then for the Y, like the object named as Y, we actually only has 1 dimension because it's not really a data frame. It's actually a series object, so it only has 1 dimension. And that's representing 150 observations or 150 rows. Now, I already explained about the train test split. So you guys also learned about that in your lecture slides. So here, the train test split is really about dividing the data into two parts, one being training and the other being the testing data set. So in Scikit-Learn, luckily we have this train test split function readily available. So let's just import that train test split, and we can actually easily partitioning our data into two parts using this train test split function. So for the train test split function, we are inputting 4 parameters here. So the first parameter is going to be x. So remember, that's our features, and y, that's our labels. And then we set the test size to be equal to 0.4, meaning that we want the test data set contains 40% of the data. And we set random state being equal to 4 because this train test split function is somehow like dividing the data set randomly. So essentially, we don't want our results to change whenever we run the notebook again. So that's why we set a random state that sort of basically fix the partition. So whenever you run the notebook again, the partition is going to be the same. So that's how the random state works. So you can set it to 4, 5, 6, or 7. But of course, if you change the number here, that means that your partition is going to be different. So 4 and random state being equal to 5 are going to be two different partitions. But as long as you keep it as 4, then your partition is going to be the same whenever you run the notebook. Now, here let's print. Oh, sorry, I forgot to discuss about the outputs of this function here. So we have 4 outputs. The first output is going to be xtrain. So that's just the training data set for the features. So that's why it's called as xtrain. And then we also have xtest. That's the testing part for the features. And then we also have ytrain. That's a training part for the outcome variable. We also have the output, which is ytest. That is the testing part of the label. Now let's check if our data is correctly partitioned. Now let's print the shapes for the training data set. Sorry, I didn't execute that. So let's also print the shape for the test dataset. So as we can see, so the test dataset contains 60 observations. That's exactly 40% of our total dataset. So our total dataset contains 150 observations. Now, what we are going to do here is that we are going to feed the model on the training set, and then we are making our predictions on the test set. So the whole reason why we are making predictions on the test set is that we are trying to evaluate the performance of the model, whether the predictions are close to the actual labels or not. So let me get back to the codes here. So when we are doing training, we just use the fit method again. So we use knn.fit, and we are fitting based on the training data set. So we are inputting xtrain and ytrain. And then when making the predictions, as I said, we are doing the prediction based on the testing data set. And here, when we are implementing the predict method, we only need to use the features. We don't need to use the labels for the test data set. So here we let ypred, we let this object being equal to knn.predict xtest. Now, as I explained, the whole reason for making the predictions is about evaluating the performance, is about evaluating whether the predictions are close to the actual labels. So here we have accuracy score, like from Scikit-Learn. So accuracy score is actually about so it's a ratio. It's a ratio of the total correct predictions divided by the number of all the observations. So basically correct predictions divided by total observations. So that's the definition for accuracy score. Accuracy score is readily available from Scikit-Learn. So what I want you guys to do is that from Scikit-Learn, from sklearn, you have to import matrix first, because accuracy score it's located inside the matrix. Then we are directly using the accuracy score. So here we just let matrix dot accuracy score, and then for the two inputs we are inputting. Of course, you can see that the second input is actually the predictions we generated earlier, right? So ypred, and the first input is going to be our actual labels. That's going to be ytest. Sorry, I didn't import the matrix first. Now let me execute that line of code to import the matrix, and yeah. Now let me get back to this line here. As you guys can see here, basically you are having the accuracy score of 0.983333. So here, this is the so-called out-of-sample accuracy, because you are making out-of-sample predictions and you are calculating the accuracy based on those out-of-sample predictions. Now let's go to the k-faults cross-validation. So as I explained earlier, the whole purpose of doing out-of-sample validation is that we want to reduce overfitting risk. So another fancier way would be the k-faults cross-validation rather than the simple train test split. So here, this cross-validation is trying to divide the data into k-faults. Actually, it's also doing the training for k rounds as well. And for each training round, it's going to randomly take one fault, one part of the data set as a validation data set, and take the rest of the data set as a training fault. So the rest k-1 faults are going to be the training data set. And so we are repeating that process for k times. So for example, for this first round, we are picking the first fault as the validation data set. And then for the second round, we are picking the second fault as the validation data set. And then for the third round, we are picking the third fault as the validation data set. And so the core idea of this k-faults cross-validation is that after doing those k rounds, we are actually taking the average performance of those k different validation faults. So it's taking the average of this first blue cell, the second blue cell, so on and so forth until the case blue cell. So what I'm trying to say is that for each of the round, the training is done on those gray cells, and then the validation is doing on blue cells. And also the performance evaluation is based on those blue cells. And then after doing all those k rounds, as shown on this figure here, we are taking the average performance of all those blue cells. Now let's try to do this k-faults cross-validation. So k-fault cross-validation is better than a simple train test split, because for a simple train test split, we still have the risk that our performance is only limited to this selected test data set, right? So still our overfitting risk is somehow high. So at least it's higher than this k-faults cross-validation. Our performance is actually determined by the selected test data set. So For example, like we have test set 1 and test set 2, and actually it might be the case that test data set 1 and test data set 2 can generate really different performance measures. So that's a risk we want to avoid by using k-faults cross-validation. So we don't want our performance measure being too reliant on the selection of the test data set. So that's the whole reason for the averaging here. So for the random selecting of the test data set and also the averaging. Now that's enough about the intuition here. Now let's get our hands dirty. So luckily, we again have this k-faults validation readily available in Scikit-Learn. So it's located inside model selection. So from sklearn.model selection, we are importing cross VAL score, and then we just create a new object here called as scores. Like we let scores being equal to cross var score, and then the 4 inputs are the k and n. Remember our model, and then x and y. So x being the features and y being the outcome variable. And we set CV being equal to 10. So this CV parameter here, that's corresponding to the k here in the figure. So it's representing how many faults we want to partition our data set into. So because we are specifying it being equal to 10, it basically says that we want to divide our data set into 10 faults. So that's our scores. Because we have 10 faults, right? So essentially, we also have 10 values for the accuracy score. Each of the value is corresponding to a single blue cell here in the figure. So that's a performance of each single blue cell. Now we want to formatting that better, and also we want to see the basic descriptive statistics for those scores. Then we set accuracy being equal to this data frame here, and then we just use the describe function to get those descriptive statistics for this array, for those 10 values here. Let's do that. So as we can see, the mean value of those 10 observations of the accuracy scores is 0.97. And also the standard deviation is 0.03. The minimum value is 0.933. And also we have the first quantile, the second quantile, so on and so forth. We also have the maximum value. If you go back to this figure here, the performance is merely the average of the performance of all those blue cells. So it's just going to be the mean value here in this table. So 0.973 is going to be the average out of sample accuracy. So that's k-faults validation. Now onto the hyperparameter tuning.